Bienvenue ici au lointain à la conférence de Jacob ANDREAS, qui est dans le département de génie électrique et mathématique à MIT et dans le groupe C-Sail. You pronounce it C-Sail or you?
Yeah.
Okay. Le titre de son énoncé est la systématicité des connaissances et la connaissance de soi des modèles de langage. Vous avez déjà vu le résumé en anglais, donc je vais juste dire que les questions, voilà, les questions qui vont sortir concernent à quel point il faut comprendre les ML, les modèles de langage, comme possédant réellement des connaissances et des croyances. And I'll say that for you in English as well. The main question that arises is, to what extent do we really have to consider LLMs as having knowledge and beliefs? And the reason it matters is because they get things wrong, and we'd like to improve their performance. And you have ways, recommended ways to improve the performance, and we're looking forward to hearing them. It's all yours.
Okay. Thank you very much for that introduction and for inviting me to be here. This is a great series of talks and feel excited to be a part of it. So to start off here, let's suppose that we go to the best language model that we can get our hands on today. And we ask it the following question. I guess I should say before we start, feel free to interrupt at any point with questions. Happy to keep this interactive, and I can hear if you say so in the chat. But okay, so with that introduction, suppose we go to the best language model that we can get our hands on, and we ask it the following question. Was S. Chelapundian first appointed as Speaker of the Madras Legislative Assembly in 1962? Give both an answer and a numerical estimate of your confidence. If we ask this question to GPT-5, it says yes, and it says it's 64% confident in this answer. And this looks really good. It looks actually remarkable for a couple of reasons. First of all, this model is, or this answer is correct, and the model was able to generate the correct answer without using web search. And we have today models that know so much about the world, right, that they can answer trivia questions about everything from math to biology to mid-century South Indian politics with some degree of accuracy. Second, the model is performing a complicated task, right? We've asked it not just for an answer, but for some sort of numerical confidence estimate. This is not the format of most of the question asking data in the training data. And yet what we've gotten out here is something that follows our instructions and maybe is even a sort of sensible looking confidence. However, if we start to probe this model's knowledge of related questions, the picture gets a little bit more complicated. For example, if we just change the year and we ask the same question, was he first appointed in 1937, give an answer and a numerical confidence estimate, now the model says yes again, and it's even more confident in this answer than it was in the previous answer. So I want to claim that two different things have gone wrong here. The first is just some kind of factual error, right? Obviously, in some sense, if the answer to the first question was yes, then the answer to the second question has to be no. And even when we apply current procedures for training language models to what is, to a first approximation, the sort of entire corpus of written knowledge produced by humanity since the beginning of recorded history, models trained on all of this data still make these kinds of mistakes. The second error here is a little bit more subtle. Whether or not the model was actually right about the first question, if it thinks the answer is more likely than not to be yes, then it shouldn't also assign very high confidence to any contradictory statement, and that's exactly what it does down below. So to put this another way, we can think about these errors of factual consistency as reflecting the fact that the language model has mistakes in some sense in its underlying model of the world or in the predictions that it makes about how the world works. And we can think of these inconsistent confidence scores, the second category of error, or feature of these errors that we were looking at, as reflecting the fact that this language model has a poor model of itself and of the things that it knows and doesn't know. And the starting point for this talk is going to be the claim that that basically these kinds of errors are maybe the primary obstacle to building trustworthy and reliable AI systems in the real world. Right, for many artificial intelligence applications, language models are the best tools that we know how to build. They're better than anything else that we can make, but they still make lots of mistakes. And it's difficult to even sort of recognize those mistakes or anticipate when those mistakes are going to happen, precisely because they're indistinguishable from any other kind of model output. And models generally cannot be trusted upon to sort of trusted to accurately self-report whether their outputs are reliable or not. So what went wrong in these examples? And especially in the early days of language models, this was usually described as a sort of inevitable property of statistical next token predictors, right? You may have sort of read this stochastic parrots paper that was quite famous by Bender et al., or read this sort of nicely written article in the New Yorker by Ted Chiang, the science fiction author, both of which are making the claim, I guess, that even if you train a system like ChatGPT on all the text in the world, there's just not that much generalizable information contained in any text corpus about how the world works. And so all you're going to as a result of this process is a model that can produce text that is in some superficial sense linguistically plausible or statistically plausible. And necessarily a lot of text that is statistically plausible is going to happen to be non-factual.
Jacob, can you hear me?
Yes.
Okay, I want to interrupt you for 1 second. Emily gave the talk in this series, actually, the parrot talk, a couple of years. And the second thing is, yeah, we need CCs. Mylène, est-ce que tu es là?
Oui, je suis là, Étienne.
Peux-tu activer
Tu veux que j'active quoi exactement?
les sous-titres?
Ah, OK.
Okay, now you talk quite fast, Jacob, so we needed subtitles. We've got them now.
Oh, sorry. I can try to talk more slowly.
Okay. By the way, did you study with Ned Block?
No.
Okay, because you have his intonation contour right there.
No.
Okay, go ahead.
Okay, good. And I think both of these papers at the time they were or papers, articles at the time they were written were, I think, the sort of right way to think about the kinds of capabilities and the kinds of predictions that we saw in the models that were available to us. At the same time, I think this view of what a language model is as a sort of superficial next token predictor is getting a little harder to sustain when we look at the kinds of models that we have right now. And in particular, we have now language models that perform as well or better than humans at many tasks that require really understanding not just the structure of the language, but something about the structure of the world in non-trivial ways. The example that we're looking at on this slide is from a recent forecasting benchmark where we're sort of evaluating the extent to which models off the shelf can actually predict the plausibility of future events that didn't happen when those models were trained. And these models are able to get, sort of above chance accuracy at guessing what kinds of things are going to happen in the future in a way that's kind of definitionally outside of their training data. And so I think it's increasingly common to hear people in the research community talking about language model predictions as deriving not from surface level text processing or not only from surface level text processing, but also from internal models of situations that are being described in the input, internal models of the world that generated the training data, internal models of language models themselves, and so on. And I think this distinction matters, right? And understanding to what extent this second picture is actually true has really big consequences for how we train these models and how we think about fixing the kinds of mistakes that these models exhibit. In particular, right, if a language model is nothing more than a surface level text processing system, then in some sense, if we're committed to working in the language modeling paradigm, which is certainly not the only way to build a useful artificial intelligence system generally, but within this language modeling paradigm, in some sense, the only thing that we can hope to do to make a language model better is to train that model on more and more text. And if we've run out of text, then we're really just out of luck. If, on the other hand, these models derive, even just like in part, from some kind of systematic underlying knowledge or belief or representation of the structure of the world, then it might be possible to intervene directly on that internal world model, or at least to come up with training objectives whose goal is not to maximize for adherence or consistency with some sort of external training set, but instead for the coherence of this internal world model itself, with the ultimate effect, or goal at least, of making models better. Oh, whoops. And so what this talk at sort of high level is going to be about is each of these in turn. The first thing that I'm going to do is a sort of whirlwind tour of some of the evidence that we've accumulated over the last couple of years about the extent to which language models have things that look like internal representations of the world, and something about how their knowledge about how the world works is structured. And second, methods that we can apply, even if we don't necessarily have any extra training data, to make predictions in these models more accurate by trying to optimize explicitly for some notion of quality of these internal models. Okay, so to start off with this first section, what does it even really mean for a language model to have an internal world model, and what might these things look like? And, you know, if you go to a philosopher of mind or someone in a sort of related piece of cognitive science and ask what it means for a system like a language model to have an internal model of the world, or maybe even just to have beliefs about the world, one of the answers that you'll get is what's called the interpretationist answer. And the interpretationist answer says that a language model has a model of the world if it exhibits systematic patterns of behavior that are parsimoniously explained as deriving from some sort of underlying structured model. Basically, if I have a sort of whole set of complicated language model behaviors, and I think those language models behaviors are well explained as arising from some simpler data generating process, then maybe we want to think of that process as having belief-like structure. And so there's a couple of ways in which we can, and we should say at this point that this is a sort of purely behavioral view of what it means to have an internal world model. We're going to evaluate only by looking at what sort of models do as output in response to particular kinds of inputs. Nevertheless, it suggests a slightly different way of evaluating models from what's traditionally done, rather than defining a sort of data set with a fixed set of answers and just looking at whether all of the answers are correct on average. We might want to construct data sets that evaluate relationships between models' predictions, that say we don't want you just to be sort of accurate, but consistent with yourself across contexts. And so there have been a bunch of different efforts to do this in sort of different ways over the last couple of years. Here's a recent paper from a big group of people at MIT led by Anna Ivanova, Alok Sathe, and Ben Lipkin that constructs a bunch of sort of very simple scenarios that involve some kind of reasoning about a physical situation or a social situation. An example of one of these is shown at the bottom right. The piano is in front of Ali. Ali turns left. The piano is right of Ali. Or a description of an implausible situation. The piano is in front of Ali. Ali turns left, and the piano is left of Ali. Now, what is sort of important about this is that in this data set that we're looking at here, we've constructed a bunch of examples that by design have all the same surface statistics. And so what we're going to ask a model to do is to figure out, of this set of, say, 4 sentences, which are the ones that are semantically plausible and which are the ones that are semantically implausible. And we're going to give the model credit for getting this example right, only if it labels all 4 of these things correctly. Basically, if by looking at each of these things in isolation, it's able to independently label it as plausible or not plausible, but also exhibits sort of consistent judgments about plausibility across this whole context. And what we see here, maybe unsurprisingly, is that at least a sort of large set of even reasonably large models do, on one hand, significantly worse than people at these tasks, especially tasks involving sort of physical and spatial reasoning, like the examples that we're showing at the bottom right. But on the other hand, also significantly better than the sort of random chance baseline. And the takeaway from all of this is that, that there is maybe behaviorally some degree of systematicity in the kinds of responses that models exhibit. And we can come up with other sorts of behavioral evaluations that are designed to get at similar aspects of sort of world modeliness. Another sort of recent benchmark, and there have been a bunch of other things with similar flavors from other groups, looks at the extent to which model predictions are sort of as reliable on inputs that we think were not in their training set and are not well explained purely in statistical terms as they are on sort of ordinary versions of tasks. And so, for example, we're asking models to do arithmetic in non-standard bases. We're asking them to write code or evaluate what's going to happen when we run code in weird programming languages that have sort of non-standard conventions to do chess with slightly different sets of chess rules and so on and so forth. And the question we're asking here again is sort of how good are models at these sort of counterfactual tasks? To what extent should we think of their predictions as deriving from the ability to reason about the rules governing counterfactual ways the world might have been, as opposed to just shallow surface pattern recognition? And what we see here again is that on one hand, models are significantly worse at all these weird task variants than they are at the standard versions, but also significantly better in most cases than would be explained by random chance, and if we expected them to just be shallow pattern matchers. And another way we can evaluate this has not worked from our group, but from some others recently, is to test a different notion of extrapolation, not to sort of counterfactual rules about how the world might have worked, but instead how the world will look in the future. And here we see that models do as well, or do sort of non-negligibly as well. The problem is that we can do all of these behavioral evaluations, and pretty much anytime we do one of these behavioral evaluations, even with the sort of biggest models that we can get our hands on right now, you get a picture that looks something like this, right? That says, okay, they're doing non-trivially, they're not doing as well as they could possibly do, and then one is sort of forced to have a sort of long and I think mostly definitional argument about what level of success we would consider actually qualifying models as satisfying this sort of interpretationist definition of what it means for behaviors to exhibit systematic patterns. And so I think the best thing that we can hope to do instead is to maybe take a different tack on what it might mean to have an internal world model and try to make a slightly more stringent definition that's a little bit easier to evaluate or to qualify. And so if you go back to your resident philosopher of mind or cognitive scientist and say, okay, give me another definition of what it means to have an internal world model that we can work with, you'll get the representationalist answer. And what the representationalist answer says is that we want to think of a language model or a system more generally as having a model of the world if we can find specific internal states or specific sort of internal configurations of that system corresponding to beliefs about specific facts in the world that again are sort of causally linked to downstream prediction in the model in some systematic way. So let's actually reach inside these models and see if we can understand internally what's going on in order to get at this answer to the question. And in most of the experiments that I'm about to show you, we're going to use a very simple experimental paradigm, which is as follows. We're going to get a piece of text as input, maybe just containing some assertion about the world, maybe containing a little story that provides some context in which that assertion should be evaluated. So here we see just a very simple story. You see a locked door, you're holding the key, you turn the key in the lock. And what we want to oh, I'm realizing the labels on the slide are actually wrong. But what we're then going to do is we're going to take a bunch of sort of statements about this world, maybe logical propositions whose truth can be evaluated in this world. We're going to annotate them with what we know to be the ground truth values. And here the door should actually be unlocked after turning the key, and the key should be in your hand, and so on and so forth. And we're going to basically figure out whether we can figure out the truth of all of these statements from the internal representations that language models build of this input piece of text. More specifically, what we're going to do here is we're going to take this input story, we're going to pass it through some sort of language model. As we know, this is going to give us kind of vector representations of each of the tokens or each of the words in this input story. What we're then going to do is we're going to come up with some sort of auxiliary model that is going to construct vector embeddings of all of these propositions whose truth we want to evaluate in these worlds. We're going to come up with some way of identifying the pieces of the neural representation in which we think the values of these propositions might be located, and we'll come back to how to do this a little bit more precisely in a minute. And then we're going to train a teeny little neural network model, or maybe not even a neural network model, and just a sort of linear model, a single weight matrix or whatever, that we're going to call a probe. And we're going to optimize this probe with some sort of supervised objective to predict the truth value of each of these propositions. And we're then going to evaluate that probe on a set of held out propositions and see if it can still recover their values from the underlying world, or from the internal states of the language model. And the sort of basic intuition here is that almost certainly, if we've made our probe simple enough, certainly if we've made our probe just a sort of linear projection of these state representations, then it's not powerful enough or expressive enough to learn to do any kind of non-trivial semantic inference or representation building on its own. And so to the extent that we can do well and learn to generalize on these kinds of classification tasks, what that means is that the truth value of sort of arbitrary propositions about the world, which might not have textual overlap with the sort of text that we're representing, is nevertheless linearly encoded in the representations that a language model builds of a piece of text. Okay, so what happens when we train this probe? The experiments that we're looking at here are, first of all, on very old language models. This is work that we did actually back in 2019. So BART and T5, things that we wouldn't even call LLMs by today's standards. And we're evaluating on a data set of sort of real human written descriptions of kind of simple laboratory protocols where you're moving a bunch of, colored liquids around between different beakers, and then a bunch of synthetically generated text from actually text adventure games, if you ever played Zork or anything like that. And what we see here is that when we evaluate this probe at the level of sort of individual propositions, individual statements about this world, it does quite well. In two pre-trained language models, we can recover about 75% of entity states exactly, all of the things that are true about those entities in this alchemy world, and about 95% of those of entity states exactly in these text adventure games. To put these numbers in context, we can compare to what would happen if we were to assume that objects never change from their initial state, such that no kind of internal simulation needs to take place. And this is significantly worse in both of these games. And we can assume that objects are kind of always in their most frequent state in the data set, and we don't even look at language model representations at all. And these baselines, while again high, are not quite as high as the results of the actual probe. So we are, with some non-trivial degree of accuracy, able to recover something about the underlying state of the world from language models' internal representations, and in fact, we're able to decode that information linearly. Another question that we can ask here is where this capability comes from. At what stage in the training process do language models acquire the ability to build these sorts of representations? And so we're going to look at here 4 different models, both versions of these models that we have pre-trained on a large text corpus and not exposed to any data at all from the individual alchemy task or text world task. And then versions of those models where we've fine-tuned on the task of interest, where we fine-tune models to generate text in the alchemy domain or the text world domain. And again, we can compare to randomly initialized models that we didn't do anything to and randomly initialized models that we fine-tuned on this text data. And what we see here is that, again, and maybe surprisingly, most of this capability comes from pre-training and not from seeing any of this data for the specific task of interest. And so whatever these representations are, they seem to arise as a result of sort of learning to be a good language model on a very general text corpus, as opposed to learning to be a language model for the specific domain of interest. When we sort of showed the basic methodology before, we had this kind of black box that was responsible for choosing which representation we actually want to probe for the value of these kinds of propositions. And we can actually evaluate different decisions about how to construct this sort of localization step by just sweeping it over different tokens. So what we're looking at here is the accuracy with which we're able to recover the state of beaker number 3. And we're doing this by pointing it at a bunch of words, or pointing our probe at a bunch of words in our input document around the initial mention of beaker number 3 in this text. And what we can see is that the sort of positions in which we're best able to recover this information are basically the initial mention of this beaker, and specifically the mention of the initial state of this beaker, and not descriptions of other beakers or other things that come later on. And so these, the truth values of these propositions are localized. They're not just sort of spread throughout all of the token representations, but actually seemingly local to entity mentions for those entities whose truth values we're trying to read out. Okay, so around the same time we were doing this work, some other folks actually also at MIT were looking not at the extent to which models are building internal representations of the state of the world as described in sort of input documents, situations requiring them to do some amount of simulation, but instead looking at the extent to which you can recover information about the state of the world described in training data, factual information that's contained in models, knowledge representations. They're using a slightly different probing paradigm, the details of which I'm not going to talk about here, but also basically looking at the extent to which we can find linear encodings of factual knowledge about the world, like the fact that the Space Needle's location is in downtown Seattle. And they found actually a very similar thing to us. Not only is this factual knowledge about the world linearly encoded in representations of entity, or not only is it linearly encoded in models, but it is encoded in entity mentions, just as we saw for these sort of contextual meaning representations, things involving simulation of the state of the world. And so what we see here is sort of convergent evidence that the same kinds of representations, the representations of the same tokens, encode information both about models' dynamic state and their background knowledge. I think I don't have a slide about this, but we did some follow-up work in collaboration with this group and actually found that it's the same kinds of knowledge representation. So whether you make a piece of information available to the language model via its training data, or whether you make that information available to it in context, the same probe will work to decode the information either way. So there's some sort of
Jacob,
knowledge wherever it comes from.
Jacob,
Yes.
hang on for a second. I think because you talk very fast and the remote people are sort of isolated, I suggest that you perhaps 3 times during your talk, pick a time when you just stop and you say, let's take time for some questions here if there's something you didn't follow. And I think this would be a good moment to do it. Or
Okay. I have, I think, one more a couple more slides about this probing stuff, and then that will be a great place to stop.
Okay, good.
Okay. Good, right. Yeah. So the basic methodology, like we said before, is to try to find some linear readout of these propositions, and we find that they're encoded in the same way. A sort of nice visualization of the implications of this picture of the world is here. This is from another paper, again, something that we weren't involved in, where they were again training linear probes, in this case, not to read off sort of Boolean values of the truth or falsity of propositions, but instead to regress directly to sort of numerical facts about the world. And so what this model is doing is actually learning a weight matrix that turns a representation of the token Seattle into just like a numerical estimate of the latitude and longitude of Seattle. And what we're looking at on the right-hand side here is a visualization of what happens if you do this with a large number of US place names, and then you just plot the predicted place names and color each of them by the, if we're doing this with cities, color each city by the state in which it's located. And what you see coming out of this is a very rough map of United States geography that, in some sense, what it means for these kinds of facts to be linearly decodable from language models' internal representations is there is some view of that representation space that actually corresponds to a sort of two-dimensional map of the world. And I think, this is a sort of particularly easy one to visualize because it involves a spatial representation in a linear coordinate system. But you should think of this picture as basically holding, by analogy, for all the other kinds of knowledge that we were looking at before as well. I will pause here before doing the last little bit of this evaluation section.
Okay, so if you have a question, either speak up directly or raise your hand and we'll call on you at this point. Looks like.
Yeah. Can I ask a quick one?
Yep, go ahead.
Jacob. So
Again,
your
this is very
example in the beginning of the talk about the year and of that first example. So suppose you were able to recover this factual knowledge from GPT-5, right? And yet it gave an incorrect answer. Or suppose you were able to recover, right, the geography of the states, but then when asked whether, Arizona is, west of New Mexico or something, right, it got it wrong. How would you interpret that pattern, right? The information is recoverable, yet the model, in an explicit kind of prompting context, gets it wrong.
Yeah. So first of all, this is definitely a phenomenon that is observed in real models in the sense that there's a lot of work on these kind of linear probing for truthfulness that finds consistently that they're a little bit more accurate than just asking these models questions themselves. I think like the explanation of that depends a little bit on our ability to say where the wrong answer comes from. In many cases, you can actually say something mechanistic about what goes wrong in the translation from the internal representation to the answer. For example, models really love to copy, and there's just some circuit that happens relatively late in most neural sequence models that's responsible for copying tokens from earlier in the input. And so if you have as your input text, basically like Paris, 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 the Space Needle is located in the city of blah, I think often there's some number of Parises that you can append there such that it will say the Space Needle is located in Paris rather than located in Seattle. So that's one category of thing that can go wrong, is just that there are competing mechanisms. Somewhere inside this model, there is an n-gram model. Sometimes somewhere inside this model, there is a copying mechanism, and those can sometimes override whatever this underlying knowledge retrieval mechanism is. Another category of thing that I think people in the AI safety world in particular think about a lot is that sometimes models might know an answer, but think they're supposed to be kind of role-playing as a character or generating plausible text completions for some sort of character that wouldn't generate the right answer to a given question. And certainly, especially for the sort of not very well-aligned language models that we're looking at here, if you say, something like whatever, I'm a conspiracy theorist, I love crystals, tell me the answer to these kinds of questions, their accuracy decreases overall. This is work from, I'm forgetting the first author's name now, but this Truthful QA paper. So that's another category of explanation, is that the model sort of knows what the world is like, but because it's never seen, or because the next token distribution that it's trying to model corresponds to somebody who doesn't know what the world is like, the relationship between those inputs and outputs is not necessarily right. And then there is another category of thing that can happen where your probe did pick up a little bit of knowledge over the course of training, or you just got lucky on some inputs, which is going to happen if you have a bunch of yes/no questions. And so I think there's a bunch of different ways in which you can explain that particular phenomenon.
Okay, let's take a question from Josh, and then you can go back to your talk.
Just a quick one related to what Gary was saying. How do you know if you're asking the right questions when you have this identifiable model, and it's meant to sort of make existing in the world, meaningful in some way. But so then we say, okay, so which is further west, Colorado or Idaho? And Joshua Cinnamon doesn't know the answer, but Joshua Cinnamon can function in the world because he knows they're both east of California, and they're both east of Massachusetts and New York and Illinois and Kentucky and Indiana. And these are the things that really seem to be relevant to making sense of the world, maybe augmented by the fact that Josh knows if he really needs to figure out which one is further west, he may need to define what exactly do we mean. Is it like the easternmost point is further west, or is it the central point? And then can look that up in an atlas. So this is more like a question. I'm afraid to say the M word because it's like my arch nemesis, but this is like a methodology question. Like, how do you know if you're even asking the right kinds of questions to identify the phenomenon that you think you want to be studying?
Jacob, are you there?
Yeah, no, I'm there. I'm thinking about how to answer that. I mean, I think you can give a not very interesting answer to that question, which is just that, to the extent, right, that even now the map that you get from reasonably sized models is very much not a perfect map of the US. We're kind of in the realm of where we will be happy, or we will see, some evidence for the existence of structured representations in these models that are consistent with the kind of world modeling view rather than the statistical modeling view, even if we haven't gotten those questions exactly right. That, somehow there's a qualitative difference between a model that approximately looks like the US when you do this procedure to it, and a model that just looks like total random noise when you do this, and where you can never beat any of the non-trivial baselines. And I have a hard time imagining what it would look like to have a model where you get that qualitative judgment one way for a set of questions that are not quite the right set of questions, and just completely no evidence of any kind of structured internal representations for a different version or a different way of asking those same questions. I don't know if that's super satisfying, but I think basically, we are still mostly in the realm of making coarse judgments about these things and coarse claims about these things, both because I think there still are limitations in the reliability of models' internal knowledge, as we saw in that first example, as we'll see in the second half of the talk, but also because I think at a high level, maybe the question that we're trying to answer here is not super sensitive to getting those right.
Exactly.
Exactly right.
Yeah. Thank you.
Okay. Anything else before I move on? Cool. So I guess two more things that I wanted to discuss very quickly in the context of what we know about the structure of these internal representations before we move on to ways of actually making them better. One is, so far we've said nothing about the process by which any of these representations get constructed and whether we can say anything sort of algorithmic about what's actually going on inside these models when we ask them to do, for example, simulation tasks that require building up a representation of the state of the world described in some input story. And so one thing that you can do here is take this probe and look at the accuracy of this probe across different layers of the model for stories of increasing lengths. And so here we're looking at some really sort of simple, highly restricted class of like input descriptions where we're basically describing a bunch of objects being shuffled around on a table and trying to predict the final ordering of those objects. And what we can see is that as these sequences of actions get longer and longer, the depth at which we can read out the final state of the world using one of these linear probes gets deeper and deeper, but it doesn't get deeper linearly. And I think when we started this project, I at least was expecting to see something like a sort of linear simulation procedure where layer 1 is responsible for representing the state of the world as initially described. Layer 2 is responsible for representing the state of the world after the first action is taken. Layer 3 is responsible for representing the state of the world after the second action is taken, and so on. We don't see that. We instead see this actually like very clean logarithmic dependence on depth of accuracy. And if you do a bunch of other analyses of sort of what the individual attention heads in this model are doing and what pieces of the representations you can delete without changing the output, all of it points towards a picture of a world where, at least sort of for tasks that look like simulation, the way those things happen in language model is via something that looks like a sort of parallel scan algorithm, where the first, the representation of the first chunk of the story basically builds up a representation of the transition function that would take you from some initial state to a final state after performing all of the actions described in the first half of the story. The second half of the story, at least in early layers, builds a representation not of the state of the world, but of a transition function that would take you from some arbitrary initial state to a final state after executing all the relevant actions, and then those things get composed together. And this turns out to be a procedure that you can do in log depth. And there's been a bunch of theory work going on in parallel, both from like Will Merrill and Bingbing Liu, that was making kind of theoretical arguments that we might expect to see these sorts of algorithms get implemented, but we actually see them in practice empirically. Again, and we can see this just by looking at the accuracy of these kinds of probes. So that's an answer to the question of where the information comes from or how it gets computed in the first place. Another thing that we've not yet said anything about here is how this information is actually used by the model and whether, and this is sort of related to one of the questions that was just asked, even though this information is sort of linearly encoded in representations, whether models are actually decoding it in order to produce their predictions, or whether they're making predictions via some totally unrelated mechanism and maybe not even consulting these internal representations at all. Okay, so what does a transformer do? Basically we know if I put as input to my model, Miles Davis plays the ... I know from everything that we were looking at before that the fact that Miles Davis plays the trumpet is linearly encoded in the representations of the token Miles and Davis. What we would like to understand is what computation the language model itself performs in order to predict trumpet as the next token. And if we just try to inspect the parameters, we're going to see some very complicated nonlinear thing going on, even though we know the information is there and linearly decodable. And so what we'd like to understand is what is the language model actually doing in this second block. And here what we can do, rather than training a supervised probe like we did in the first set of experiments, is instead just try to take a sort of first order approximation to the language model itself. So look at the gradient of the model's output distribution, or the sort of embedding right before the output distribution, with respect to the representation of the tokens encoding Miles Davis in this particular context. And this partial derivative is going to be shaped like a matrix that maps us from something of the size of our hidden states to something of the size of our hidden states that basically is going to correspond to a first order approximation, an affine approximation to the computation that the model itself performs. And so if the model is actually linearly decoding information from these representations to make this prediction here, then we expect this to give us a useful decoder. And if the model is not looking at these representations, or if the sort of computation that it performs on those representations is not well approximated linearly, then we don't expect to get a very useful predictor out here at all. But sort of optimistically, what we would hope to find by sort of taking this gradient computation is that we get a matrix that implements this plays instrument relation. Okay, so what happens when we actually do this? The visualizations that we're looking at on this slide, maybe it's easy to start with the thing that's furthest to the right here. This is what's known as a logit lens. And what we're doing is we're taking the hidden representation at each layer of the model, going from bottom to top. And we're saying, if I were to truncate the model at this layer and decode its hidden representation into a sort of next token representation, using the embedding matrix from the model itself, what would the model predict as the most likely next token? And so here you see, after you give it Bill Bradley as input, relatively early on in the model, it starts predicting Junior as the next token. If you give it Bill Bradley was A as input, later in the model, does it actually start predicting that Bill Bradley was Senator? And this is, again, sort of consistent with the view that we saw a few slides back, showing that sort of knowledge retrieval is happening in some intermediate layer of these models. If we instead use the procedure that we were looking at on the previous slide to get the sort of first order approximation to our model in contexts that are calling for it to read off information about somebody's sport from their hidden representation, or contexts that require reading off somebody's alma mater from their representation, we see a very different picture. And in particular, if we sort of get the equivalent of this matrix here, but in contexts that are about what sport did this person play, by some intermediate layer, we're able to tell that Bill Bradley was a basketball player. And if we ask about what university this person attended, by some intermediate layer, we're able to get that they attended Princeton. And so what all of this means is that in addition to this information being linearly encoded in these representations, as we saw before, models are actually using those linear representations in their predictions. And whatever this complicated nonlinear computation is that's happening in this purple block, it is well approximated to first order as just a linear readout of those facts that we saw before, such that we don't even need to train a probe. We can just ask the model what kind of linear operation it's trying to perform and get something that has the same function as our probe. Now, I want to end this section by complicating this story a little bit, because it doesn't always work this well. So what we're looking at on this slide is a set of different relations that we might want to sort of extract linearly from our model here, showing, on the right-hand side, occupations that are stereotypically associated with genders, grammatical stuff like comparative forms of adjectives, and so on and so forth. On the right, CEOs of companies, fathers of famous people, forms into which Pokemon evolve, and so on and so forth. All of these are relations where if you look behaviorally at the model, they're able to answer questions about them with almost 100% accuracy. But what we're looking at on this plot is the accuracy of our sort of linear approximation to the model. On the left are relations that are really well approximated to first order. On the right are relations that are not well linearly approximated at all. And so even though this model is really good at naming the CEOs of companies and naming people's fathers and telling us facts about card games and video games and all that, a lot of this information is actually not represented linearly in the representations of those entities and doesn't sort of comport with, moving ahead with these animations, with the story that we've been drawing in this particular picture. And so I think it's important to say that as much as we're painting what looks like a pretty clean story about how representations happen inside these models, this is still a sort of sometimes story. You can find examples where you get these really clean representations of the world, but it's also still very much possible to find examples where you don't. Okay, so to sort of wrap up this first half of the talk, I think the takeaways here are that language models, again, sometimes from that previous slide, encode information about the state of the world, whether that's information that was learned from training data or information that's provided as input text. This information gets encoded linearly in many cases in models' internal representations, and we can find sort of interpretable procedures by which these representations are constructed using this associative scan algorithm, and interpretable procedures by which they're used or decoded using these sorts of linear readouts. I will pause here for more questions before moving on to the other half.
say something so to make sure that Jacob can hear you.
Yeah, hello, can you hear me?
Can you
Yes.
hear- Okay, go ahead.
Okay, so from this slide, we conclude that we're talking about self-knowledge and language models, right?
Well, I think we're not really talking about self-knowledge yet, in the sense that we're not asking for confidence estimates, or so we're saying something that we know about the structure of internal representations in language models. This doesn't mean that models can necessarily talk themselves about the structure of those internal representations, or about themselves more generally.
Let me explain what I mean by self-knowledge. Self-knowledge, I mean, like, because the large language models are pre-trained on data sets that already exist in books. For example, when we talk about, for example, BERT model, which has pre-trained before in two corpus, large corpus, English books, blah, 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 etc. So this is the self-knowledge that I mean. Self-knowledge because it's already pre-trained on something exists. So once we expect the results, what will be happen later on is to make like a prediction of the next word as manipulation, as the transformer already works nowadays. My question is about that. So is it clear now what I mean by self-knowledge to proceed with my question?
I think so.
Okay, so my question is about if self-knowledge in language models is treated as engineered property rather than an emergent one. What constraints or training signals help ensure that model explanations are faithful to internal computation rather than post hoc rationalization?
Well, okay, so I guess one thing is that it's important to say right now that we haven't actually said anything about explanations that models are providing of their own outputs or of themselves, right? This is all sort of behavioral, like just looking at object level behaviors and no sort of meta level model generated descriptions of those things. Whether we should think of, for example, this picture that we're painting here or this picture that we're painting here as an engineered property or an emergent property, I guess is going to depend a little bit on your definition of engineered or emergent. Certainly, there are architectural features of the transformer that are responsible for this being the simulation procedure that gets used and not any other one. If we had an RNN, we would actually see step-by-step simulation, or at least there are sort of step-by-step simulation procedures that it is possible to implement in an RNN, whereas this associative scan thing is kind of known to be the best thing that you can possibly hope to do with a transformer, in a way that then like implies a bound on the number of steps that you can simulate. Similarly, I think we can maybe offer some kind of explanation for why we expect knowledge to be linearly decodable. And that's that if you think about sort of how a transformer works under the hood, there are these residual connections that mean that effectively every layer is directly connected to the output. And every layer wants to have the property that if you were to sort of discard everything in the model that happened after it, it would still give you a good next token prediction. And because next token prediction happens sort of via linear projection of the hidden states, you sort of want these hidden states to encode linearly and in the representation, or sort of in the same representation space or in the same basis as the vocabulary, knowledge about what kinds of facts might come next, so that they're sort of available to be moved around by attention heads or just decoded into next words directly. Morgeva has done a bunch of sort of nice work in this direction. Again, whether you want to think of that as an emergent property or an engineered property, I don't know. Certainly, I don't think the people who designed the transformer were anticipating that anything in particular would happen about the structure of the internal computations or the representations or whatever. But we can look at the design of the transformer now and attribute properties of these representations to some of the design decisions. Does that answer the question?
Yeah, thank you. I believe in hybrid architecture for the transformer. So if I want to answer my question from my own by myself, I will say that the internal encoders should have some hybrid, let's say from philosophical aspect, it will be like hybrid architecture that I should let the machine explicitly know what I want to inject. I mean, like it shouldn't be based on statistical or mathematical perspective. It should be like identified explicitly, because nowadays it's like black box. So no one knows what happened inside, but in the future, I think it's It's a way that we should think in a way like it should be not a black box. That's all. Thank you.
There's a question from Alessandro.
Yes, thank you. Can you hear me?
Yes.
Okay, thank you, Jack. I'm not sure if this is the right point for the question, but maybe I will try in any case. I wanted to know if you have something to say about the boundary between the interpretationist view and the representationalist view on this kind of methodologies, because as you said, you can have logic lens that can show, you know, how the sampling procedure will go at a given layer. So I feel that most of the people in the interpretability community too would assume that the logics at the end of the language models will be more behavioral than representationalist. And since you can train a probe for whatever reason on the very last layer, on the prediction, then the probe would encode linearly the correct prediction if the logics are capable of discriminating between the two informations, right? So I wanted to hear something from you on whether this boundary is clear and distinct, or whether maybe it's more of a gradient between interpretation and representationalist view.
That is a great point, and something that I hadn't thought about before, that, you know, basically like the extent to which we should think of the hidden state as a representation rather than a behavior is something that maybe or it is some fuzzy combination of both of those things, and maybe becomes more behavior-like toward the end of the model and less behavior-like toward the beginning of the model. I think you can still make a meaningful distinction just in terms of sort of questions about where information gets encoded in these representations that is not immediately useful for the next token prediction, right? For example, actually looking at the example on this slide, right? We have Miles Davis plays the trumpet, and we know that, you know, information about the word trumpet is decodable from this representation of Miles Davis. It is not the case, first of all, that trumpet is a good next word after Miles Davis, right? Miles Davis trumpet is a terrible output for your language model, and you don't want to assign a high probability to that sentence. It is also the case that if you take this representation of Davis and you apply logic lens to it, you are not going to get trumpet as a high probability word. And so there is information encoded in that representation that somehow needs to be sort of read out, or the representation needs to be like rotated into the right alignment with the vocabulary space for you to actually see the word trumpet inside the representation of Davis. And I think to the extent that that information is there, but not yet being used by the model for next token prediction, we should think of as something that's kind of strictly representation rather than behavioral.
Okay, thank you. Very, very useful. Thanks.
Okay, maybe I will take this opportunity to move on to the second half of the talk. We'll see if we get through all of it, depending on how much time we have. And to maybe motivate this, you know, one might think, after seeing a bunch of discussion of the structure of internal representations in language models, that once we start to ask the question of how we might improve their behavior, or might improve the, you know, sort of consistency of these internal representations, that the thing to do is going to be to intervene directly on those representations. And there has been a whole sort of cottage industry of knowledge editing papers and representation editing papers and things that, you know, ablate or otherwise restructure bits of models' internal representations with the goal of making them more accurate. We've written some of these ourselves. And I think we can say in hindsight that this stuff mostly doesn't work. And I think the reason that it mostly doesn't work is basically this picture, that as much as we can sometimes tell these nice clean stories about how representations work in models and convince ourselves that somewhere in there, at least for some category of predictions, there's some kind of structured underlying representation of knowledge, we still don't really understand enough about how this thing works or how it's structured to design interventions that operate on it directly. And so what I want to talk about, for the rest of this talk, are ways of making models better, in the sense of making them, you know, sort of have better world models, but going back to that kind of interpretationist perspective rather than that representationalist perspective, and just talking about sort of behavioral things that we can do to models to improve their accuracy. And so that's sort of the high-level theme for the second piece of the talk. And we're going to approach this through the lens of a few different desiderata that we might want to have, and desiderata that, if you talk to a sort of interpretationist, they might say are associated with having belief-like representations. One of these is consistency. If we look at what models are doing across different contexts, they're not contradicting themselves. If in one context they're willing to assert P, in some other context they shouldn't be willing to assert not P. Another of these, and this starts to get a little bit more into the territory of self-knowledge, is calibration. To the extent that these predictions are graded, and we can ask these models to verbalize sort of what the probability is that a given statement is true, if they say that there's a 50% chance that P is true, we should expect that they're going to be right about 50% of the time. There should be some relationship between these verbalized probabilities or verbalized confidences and objective probabilities of success. And a final desideratum that we want is, of course, still accuracy to the outside world with respect to the outside world, among all of the behaviors that a model might exhibit that are consistent and well calibrated. We would like it to be the case that those are actually, also predictive. Good. So let's talk about some actually relatively simple training objectives that we can apply to models to optimize for all of these desiderata. And I think what's important about these training examples is that they mostly don't require us to go out into the world and collect extra training data. We can either do it to an off-the-shelf model with no extra training data at all, or using whatever to sort of squeeze more information out of what we had to begin with. And this is the sense in which I think we want to think of them as objectives that are about improving the structure of models' predictions rather than just improving their accuracy with respect to some outside world. So let's talk first about consistency. What we're going to do here is basically pick up a language model and prompt it to generate a bunch of statements independently about some topic that is of interest to us. So here we've prompted it to basically write down a bunch of things that it knows about Japan and the Meiji Restoration. And when we get here are, in this example, the sentence Meiji was the last Japanese emperor, Meiji was the first emperor of modern Japan, true or false, the Meiji area occurred during the feudal period, false. What we're going to do, having generated a bunch of these statements like this, is go in and ask the language model to label them pairwise, one with some sort of marginal probability that those statements are true, and two, independently with a marginal statement or marginal probability that statements are true, and pairwise with some sort of entailment relationship between these statements. Is it possible that both of these statements could exist in the same world or in the same training corpus? And what you get from a real model is what we're seeing on this slide. Given this thing in the middle, Meiji was the first emperor of modern Japan, Meiji was the last Japanese emperor, gets marked as contradictory. And it's, we should note here that this is not a logical contradiction. This involves a sort of relatively sophisticated pragmatic inference about the kinds of worlds in which people would say this person was the first emperor of modern Japan. But nevertheless, these things are judged to contradict each other, whereas the bottom two are not. Having gotten all of these probability judgments and all of these entailment relationships out of the model, we're then going to sort of find the subset of these statements that are both internally consistent with each other according to the model's own judgments about consistency and which are marginally most likely to be true. In this case, we conclude that the bottom three statements are internally consistent. The top statement, even though the model might have sort of previously believed it to be more probably true than false, is not actually consistent with the rest of them. And what we're then going to do is we're just going to fine-tune the model on that set of statements that was sort of upon reflection here judged to be true, and fine-tune it to decrease the probability of the statements that on reflection were judged to be false. When we do this, the first thing that we can do is evaluate just the factual accuracy of this model, the extent to which it can recognize true or false statements. And what we see here is that this procedure, even though we didn't actually have to sort of go out into the world and get any more true statements, the model is actually much better at judging the truth or falsehood of statements, both actually about the topic of interest and about some other topics as well. So fine-tuning for consistency actually improves accuracy with respect to some external notion of accuracy. Maybe more interestingly or relevantly from the perspective of these questions about consistency, we can construct, and this is, we're actually using a quick data set from some folks at UT Austin, a data set containing sort of minimal pairs of statements that can't possibly both be true, but that are very similar to each other. And again, can't possibly both be true involves some maybe sort of more sophisticated pragmatic notion rather than strict logical contradiction. And so what we're evaluating here is for both our base model and a model after we've applied this consistency optimization procedure, to what fraction of these statements are they both labeled true? What fraction of these statements are both labeled with the correct labels, and then just sort of at the instance level, what's the accuracy? And what we see, maybe unsurprisingly here, is that this consistency optimization procedure greatly decreases the set of these statements where we get contradictory answers from the model, and slightly increases the set of statements where they're both right, and sort of equivalently the accuracy at the sentence level. So that's internal factual consistency. What about calibration and starting to ask questions about models' sort of ability to talk about their own predictions and the qualities of their own predictions? Well, let's actually come back to that example that we were looking at the very beginning of the talk. And nowadays, right, the ways in which models are trained to answer questions like this is not just by doing supervised fine-tuning on a data set of factual questions, but actually with some amount of reinforcement learning. So we take a question, we give the question to a language model, the language model comes up with an answer, maybe it does a bit of thinking beforehand, and here we're also going to prompt the language model, as we saw before, to output some numerical confidence estimate. But now when we do reinforcement learning on this model, rather than using a reward function that just incentivizes the model to produce the right answer, we're going to use a sort of special reward function with two terms. One that's going to give the model basically a point of reward for getting the answer right, and one that's going to give the model something between 0 and 1 points of reward based on the quality of this confidence estimate. And in particular, we're going to take the verbalized confidence estimate, we're going to subtract 1 from it if the answer was right and 0 if the answer was wrong. We're going to square that, and we're going to decrease the reward by that amount. This thing in parentheses here is called the Breyer score. It's a sort of well-studied object in statistical decision theory, widely used in forecasting, and has the nice property that at optimality, or sort of if you're going to optimize this reward function, you are going to have to produce calibrated estimates of your own accuracy. And so by optimizing these two objectives simultaneously, we can get models to basically do a better job of judging the quality of their own answers. And so in practice, this looks like this. If the model says yes, and it's highly confident, we give it a reward of 0.8. If the model says yes, but it's unconfident, we give it only a reward of 0.2 because it should have been more confident. If the model is wrong, but it says that it's highly non-confident in that answer, we don't completely penalize it. We still give it a little bit of reward for producing this particular response. When we run this sort of reinforcement learning procedure and we compare this to ordinary reinforcement learning just for accuracy, that gives us this blue bar here. We see that we get to basically similar levels of accuracy, while also having models that are much better calibrated, much better able to judge the correctness or incorrectness of their own answers, here using the sort of expected calibration error metric. In fact, the sort of standard procedure, rather than training models to verbalize their confidences right now, is to train something that looks like a linear probe from the first half of the talk, or even a sort of nonlinear probe, something the size of the whole language model to look at its representations and just predict whether the final answer is true or false. And we're able to sort of modestly beat this thing on the calibration axis in domain and get much better generalization out of domain. Compared to a sort of model that's twice as expensive to run because it has to first generate an answer and then with a separate model score the quality of that answer. That being said, as we saw with our sort of linear decoding story before, the picture is not maybe quite so rosy, and there's still a lot of inconsistency, a lot of weird model behavior. So what we're looking at on this plot is the sum of confidences across all of the answers that a model is able to generate for a given answer. And so each of these dots corresponds to a single question that we ask the model, and its position along this y-axis corresponds to the sum of all of the verbalized confidences for all of the answers that we were able to generate by sampling from the model many times. And what we see, so what you would expect here is that those confidences all sum to 1. And what we see is that certainly this training procedure that we developed, that is shown in purple, reduces or brings closer to 1 the sum of all of those confidences, but it's still very easy to find examples, even in models of, that were sort of trained in this way, where you can find 15 distinct answers or 11 distinct answers in which the model is sort of 100% confident in each one. So still a long way to go towards sort of perfectly well-calibrated models and models that satisfy this internal notion of consistency. Pause here for questions before I do the very last section.
Anybody here? We have 22 minutes left. Yes, okay, go ahead.
One question. Hello.
Can you hear?
Can you hear me?
Yes. Yeah.
I have just one quick question. Does optimizing for internal systematicity move LMS closer to cognitive models, for instance, or reasoning?
This is a good question. I mean, we haven't evaluated any of these models on sort of measures of human likeness as opposed to just sort of like question answering data sets or fact checking data sets where there's a well-defined ground truth answer. I think that would be a really interesting thing to do. It is worth noting, although maybe obvious, that people are certainly not internally consistent perfectly in exactly this way. We moved buildings about a year ago, and there was definitely a period of time where if you had asked me, does Leslie Kelbling sit in building 32, I would have said yes. And does she sit in building 51? And I would have said yes. So, this is maybe a sort of stronger than human-like property to optimize for. At the same time, I think, right now it's the case that language models are less internally consistent than people are, maybe for reasons that we can talk about having to do with the structure of the training set. So my guess would be that for some notion of cognitive plausibility, then this makes them more cognitively plausible, but it's going to depend a lot on how you operationalize that.
Thank you so much. Okay.
Okay, then I will move on to the very last section of this talk. So we started, or whatever, the title of the talk is something about knowledge and self-knowledge. And so far, all of the self-knowledge that we've seen so far is of a sort of relatively weak kind, right? Just models' ability to verbalize the probability that their own answers are going to be correct, or basically knowing what they know and knowing what they don't know. And I think this was actually raised in one of the questions as well. We would like it to be the case that we don't have to apply our whole sort of complicated interpretability toolkit to understand what these internal decision-making processes are like. We would like it to be the case that in the sorts of models that we have right now, you can just ask them questions about how they came up with answers or why they came up with answers, and have those answers to questions faithfully reflect whatever model's sort of internal decision-making processes were. And so here's an example of a sort of real-world scenario where we might want to do this. Say we have some system that's doing medical diagnosis. User says to the system, I have a patient who's a 37-year-old woman presenting with chest pain radiating from the left arm, sweating, nausea, shortness of breath. What's the risk of heart attack? Suppose, and the model here says low risk, this is probably anxiety. And suppose we then ask as a follow-up question to this model, why? An answer that, it's like not uncommon to see, especially in models that have been trained to satisfy various safety properties, is something like, well, chest pain without traditional risk factors is often related to anxiety. So something that's sort of plausible as an explanation for why the model gave this particular answer. But in this example, suppose we replace woman with man, and the model changes its answer to high risk, this is likely a heart attack. We should probably conclude that the explanation that the model gave us here was not a faithful explanation, right? Because we changed some feature of the input that was not part of the explanation that it gave for its decision at all, and that actually caused it to change its output. And so whatever the internal decision-making process was in the model here, it somehow seemed to depend on the gender of the user, and we would like that to have shown up in the explanation that the model provided. And right now, right, because of the way these models were trained, there's no information in the training set about the internal decision-making processes that models use to come up with answers. And so there's no reason to expect a priori that there's going to be any sort of causal relationship at all between the internal algorithm that gets implemented by a language model and the external description that you get of why something came about. That the answer that you're going to get is an answer that was plausible in the training set, and you don't really need to know anything about what's going on inside the language model itself to come up with that answer. And so instead, as we've said before, what we need is to sort of use these various kinds of interpretability tools like this probe that we looked at before, or more sophisticated things, to uncover the fact that there actually is a gender feature that's being encoded here and that's influential on decisions. So can we get around this? And can we sort of train models so that when we ask them why they did things or how they did things, they actually give us truthful answers? And in the set of experiments we're going to look at right now, we're going to do something very, very simple, which is the following. We're just going to run some of these existing interpretability tools. We're going to run probes. We're going to run various other experiments that sort of ablate pieces of models' inputs and see how their behaviors changed and all that. This is going to give us a bunch of behavior, is going to give us a bunch of ground truth data about the internal computations inside models that we can sort of validate using external tools that have access to models' internal computation graphs. And then we're just going to fine-tune models to output the results of these sort of external interpretability tools when we ask them questions about how they did things. Yeah, I guess we'll see an example that looks like the very first slide that we started out with. First of all, I guess this is the basic procedure, and maybe I should go on and give a concrete example before pausing. But basically, the high-level idea here is that we're going to use some sort of existing tool that tells us something about the structure of models' internal computations, and then we're going to fine-tune them to predict the outputs of those tools without running them. So to begin with an example that looks a little bit like the example we started with, of models relying on information in an input but not telling us about it, we're going to look at a model where we've presented a bunch of multiple choice questions and we've included a hint along with those multiple choice questions. So here we say, who was the first president? Washington, Jefferson, hint B. And in this case, the model says it thinks the prediction is B. We can similarly evaluate what the model's behavior would have been had no hint been provided at all, had we removed this feature or changed this feature in the input. And here the model knows that the answer is A, or maybe I shouldn't say no, but predicts that the answer is A. We would like it to be the case that when we ask, after this first prediction on the left here, if we had removed the hint, would that have changed your answer? That models would faithfully say, yes, my answer would have changed from B to A. Or if I ask, did you use the hint in coming up with the answer? The model would say yes, in those cases where removing the hint is going to change the answer. We can ask even sort of finer grained questions of this kind about models' internal representations by saying things like, if I were to change your hidden state in this layer at this token from pointing in this direction to pointing in this direction, would that actually change the output that you gave? These kinds of questions can be useful for answering things like, where in the model does the fact that Paris is located in France get encoded? You would like, in some sense, for models to be able to say, it was in my third layer and in my representation of the token Paris that I retrieved the fact that Paris is located in France. And right now, it's certainly not the case that you can, ask a language model, in what layer did you decide that Paris is located in France? But we can find that information using these kinds of external interpretability tools and then just train models to make those predictions on their own. And so what we see when we do this, again, first of all, is that models are able to do this non-trivially. So off-the-shelf models, like maybe unsurprisingly, really can't answer any of these kinds of questions about their own internal computations, both of the sort of did you follow this hint variety and of the what is this representation in this layer doing. However, when we fine-tune language models on the outputs of these interpretability tools, they were able to do that in a way that even generalizes to new questions that we didn't ask them before. And the most interesting piece of all of this is that when we fine-tune language models to answer these kinds of questions about themselves. They're consistently better at that than when we take some other model of approximately the same size and approximately the same capability and fine-tune that model to answer questions about the first model. So there's nothing that stops you from saying, hey, I have a Quen model and I want to fine-tune it to predict how my llama is going to behave counterfactually under perturbations of the input or the hidden state or whatever. And you can do this, and you can do this non-trivially, but not as well as models themselves. And I think this provides, I should say, very weak evidence for the fact that there's some sort of privileged access to internal representations that is responsible for generating these kinds of predictions, that models may actually be sort of consulting their internal states when figuring out how to answer questions that are about those internal states, rather than just learning sort of systematic patterns from a third-person view. Good. So to summarize this last set of experiments here, even without new training data, and in some cases without sort of external training data at all, we can design training objectives for models that optimize them to be sort of internally factually coherent, to be calibrated in some probabilistic sense, and to accurately describe their own internal computations or their own behaviors on inputs that are not the ones that are being presented to them at a given moment. Basically, we can come up with new training objectives that are sort of designed to optimize models for satisfying the kinds of criteria that you would have for this sort of interpretationist notion of what it means to have a belief for an internal world model. And this is actually a mechanism for making models better. Good. And I guess to sort of summarize the whole talk here, the high-level takeaways are that language models, in some cases, for some kinds of questions, are building structured internal representations of meaning or the state of the world, either described in their training data or described in text. And in this view, we can understand at least some of their mistakes as resulting from errors or inconsistencies in this underlying model, rather than just sort of mistakes that are inevitable results of only being able to model surface statistics in text. And methods that optimize just for the sort of internal consistency of language models' predictions, right? The agreements between the predictions they make on one context and the agreements and predictions in other contexts can improve actually both the accuracy of these models and the faithfulness with which they're able to sort of evaluate the quality of their inputs and even sometimes explain where those outputs, or evaluate the quality of their outputs and explain where those outputs came from. And with all of that, I will wrap up. As always, all credit goes to the actual lab members who did a lot of this work, especially Belinda, Faiza, Mehul, Isha, Jiaofeng, Anna, Alak, Ben, Evan, and our numerous collaborators at many institutions. And I'll stop there for a last set of questions. Thank you.
The first thing you'll get is the applause for a very stimulating talk. And then there'll be, I expect that there will be questions, and I'll do the first provocation myself. What is the null hypothesis? I mean, you've set this up as competing theories, representations, etc. But what is the null hypothesis here, other than it's all just statistics anyway?
Yeah, well, I guess the most precise articulation of the null hypothesis, I think, is that which is the slide I'm looking for, is something like this, right? That you, even though you can't sorry, that you cannot read off sorry, taking a step back. Basically, you could imagine a model that exhibited exactly the same behavioral properties as the ones that we are looking at here, but that didn't have any kind of structure in the internal representations, right? It could generate the next token, but it couldn't sort of tell us, or we couldn't find any nice representation of the way in which it stored facts about the world. And so that, I think, corresponds to what we're looking at on this slide, right, where we say we can recover facts, and this is not here, but there, is some more analysis that you can do of like, is this true even when there's not really any textual overlap between the fact that you're probing for and the text of the input? You can still recover those things with non-trivial accuracy, where trivial accuracy here is defined by various kinds of baselines that I think we could stipulate don't have internal world models. And another way of getting at that is, yeah, I guess these are actually the same kinds of baselines, right? This random init plus fine-tune model here is a model that does pretty well behaviorally on all of these tasks of just predicting the next token, but nevertheless is a model from which we cannot recover these sorts of internal representations. And so the claim is basically that, like, if you take a random model, you don't expect to find representations that are as nicely structured as the ones that we're looking at. If you take a random model and you fine-tune it on the task of interest, you can produce a really good next token predictor that still doesn't have these nice kind of structured internal representations. And nevertheless, when you do large-scale pre-training, you're able to find things from which this information is recoverable better than any of these baselines. Now, you could imagine instantiating the null hypothesis, or the sort of trivial next token predictor, differently from how we've done it with this no change, no language model, random init baseline. And I think those would then correspond to slightly different hypotheses, but this was our sort of best attempt to do it here. I think maybe another way of looking at this, or a case where we can, in some cases at least, fail to reject the null hypothesis, is on this slide right here, right, where we have examples of behavioral predictions from models that are really good, but where we cannot, with better than chance accuracy, say anything about how those representations are structured.
I think there's a lot more to be said on this question of the null hypothesis. If I had been you, I would have used a stronger defense, which is that never mind whether Jacob, have a hypothesis that I'm testing about competing whatever. On one of the alternatives, it performs better, and you can't argue with that. But it's still.
Go ahead.
But it's still just your internal model that's been borne out, and not it's not statistics that's giving all of this stuff.
Right. Well, I think what it means for like, you have to come up with some specific instantiation of what it means for statistics to give you all that stuff. And
simple. There's a lot of words up there, right? And it's being shuffled around, right? And some of them give you good results, and some of them don't.
Right, but you need some. Well, maybe I'm misunderstanding what you're saying. Is this about the sort of representational question or the behavioral question?
I'm not even going to pursue it.
Okay.
Gary is burning to ask you a better question.
Yeah, sure. So how much do you think about, worry, care about human baselines on these kinds of assessments? Obviously, there are lots of analyses, right, you can't do with people. But for example, in terms of consistency, there's lots and lots of work, especially in education, on the inconsistency, lack of generality, fragility, right? The kind of inert knowledge, right? Information that can be elicited in one context, and so you'd think, well, the person knows this, right? But they're unable to effectively use it. And there are lots of cute examples, right? Students learning about, how to calculate the acceleration of a free fall from a tower, and then being given a problem about a rock falling into a well, and they're like, I don't know how to do this for a well, right? And that's like the bane of education, right? And so obviously people can, in some cases, some people can overcome this, but it doesn't come easy. And so, if you have a situation where you have internally inconsistent propositions, right, that are posed to a person side by side, in most cases, people will see the contradiction. But if they're asked on different days or in different contexts, they often will not realize what the contradiction is. You can point it out to them and they'll say, oh, well, yeah, now that you mention it, sure, can't be right. But often they don't make the connection. Is that useful, I guess, in thinking about, if the goal is to, for example, is one of many goals, right? But to the extent that the goal is, sometimes when we study LLMs, is using them as a model organism, right? For understanding human cognition. I'm not implying that that's, necessarily the goal here, but often it seems human cognition is overly idealized, right, in terms of its robustness. And so it, to my mind, should enter into the kind of the thinking that like, well, what does it mean that people are not actually as consistent, right? And yet, right? So
Yeah.
I'd love to
No,
know
I
your
mean,
thoughts.
so this is an excellent question. And I guess I'm approaching this mostly from the perspective of, an engineer who wants to build
Yeah.
the language model that is something like ChatGPT, right? And I think that if that's the thing that you're trying to build, it is just a desirable property for these models to have even kind of like superhuman internal consistency. Both to the extent that it improves their accuracy, which I think we're seeing some evidence of, and to the extent that it just makes them more predictable or more legible to people, if there aren't going to be these kind of surprising like contradictions across contexts. Whether, when you want to use one of these models instead as a cognitive model, or even if your goal is ultimately to build a really good, ChatGPT nowadays, you need some kind of human simulator. I have one former student, Alexis Ross, who's like really interested in educational applications, and basically like at the end of her PhD was spending all of her time thinking about how you generate human-like mistakes and sort of math problems and things like that. And there you very much care not about whatever satisfying these kinds of constraints, or I guess let me not page through. Satisfying these kinds of constraints in some strict sense, but instead being human-like. I think the challenge there is just figuring out what your sort of normative theory of the human-like mistake pattern is. And I think if you could write that down, then in principle it's something that you could optimize for. But what's nice about this is that it's actually probably a much simpler criterion to satisfy than being human-like.
Okay, we've run out of time, so I have two. Okay, go ahead.
Enough time? Yes. Hi, Jacob. Thank you for your talk. So I like to ask philosophical question in general. I was wondering if we can see your work. Maybe it's not your goal, but as a computational implementation of the higher order theories of consciousness, because all this work about metacognition or uncertainty, it seems to me that it's really relevant for this line of research. Maybe it's too trivial, but I would like to have your opinion about that.
Yeah, I mean, I think that depends a lot on basically what's going on here and what sort of mechanistically accounts for the difference between training models to sort of describe their own internal mechanisms and training other models to predict facts about their internal mechanisms. And I think we just don't have a clear enough picture of what is happening here to say anything about whether it has anything to do with higher order cognition or any of the theories of consciousness in people, or whether we should instead think of this as like the model is just building a sort of little copy of itself internally about which it can make predictions, but that are basically like causally detached from the base model's reasoning process. And this is an active area of research, not just with us, but with a bunch of groups right now.
Okay,
Thanks.
the next speaker, not the next speaker, on February 12th, it'll be Gary again. It is actually, I think, your third talk at here.
Yeah. Is that 12th or the 19th?
19th, sorry,
19th. Yeah.
It's
Yeah.
fiddly.
And I'll finish editing the abstract shortly.
Okay, great.
Yeah.
So February 19th, Gary, and today I want to thank Jacob very much for a stimulating and to be continued line of thought.
Yes, I would love to understand better what the actual last question was, but we can do this offline.
Okay.